For decades, we've been sending submersibles into the deepest parts of the Red Sea, and the deeper we go, the stranger it gets. This should be one of the best understood young ocean basins on Earth, yet in its darkest trenches sit features that look almost impossible. Perfectly still underwater lakes resting inside the ocean itself. Pools of dense, metal-rich brine so heavy they hold their shape, so sharply edged that video bends at their boundaries. These have become one of the Red Sea's defining mysteries. But here's what researchers didn't expect. The more often we return to these pools, the more they seem to change, and the more new ones we discover. Some brine pools become hotter, more acidic, or more metal-rich over time. Others develop new chemical layers. And just recently, scientists found an entirely new set of brine pools right near the Red Sea coastline, a place no one expected them to exist at all. Every new expedition rewrites part of the story, and every change raises a deeper question about the hidden plumbing beneath the seafloor. So in this dive, we're exploring how these underwater lakes form, why they evolve, why new ones keep appearing on our maps, and what their chemistry and microbial life can teach us about the Earth, and maybe even life beyond it. Stay curious, stay current, and join me on this wild ride. First, a bit more about the Red Sea. The Red Sea is geologically young, only about 30 million years old. In ocean time, that's barely infancy. It's a place where Earth is actively pulling itself apart, where Africa and Arabia are drifting away from each other along a growing rift. Beneath the surface, that stretching creates conditions where normal ocean rules simply don't apply. Volcanic ridges split the seafloor. Salt bodies thicker than our city skylines sit buried below. Faults open and close as the crust stretches, and hydrothermal fluids rise from reservoirs we still haven't mapped. Together, these forces produce brine pools, dense, toxic, oxygen-starved basins that behave like self-contained chemical worlds. Close-up shots reveal why they seem so alien. The boundary between seawater and brine is abrupt, a clean, shimmering line. No slow transition, no mixing zone, just a sharp step into a different environment entirely. Some of these lakes have remained stable since the 1960s, and probably way before that. Others have changed chemically or thermally over time as new data accumulates. And brand new pools continue to be discovered. It didn't take long for researchers to realize these pools weren't static landmarks. They were part of something far more dynamic. The earliest signs of change were subtle. When expeditions returned to previously mapped pools, the outlines looked slightly different. A layer was warmer, a metal concentration had increased. Some pools were becoming more stratified. At first, these shifts were easy to dismiss. New instruments, new angles, natural variability. But the pattern kept appearing. Not random noise, but consistent, measurable evolution. Then came the discoveries that shifted the conversation entirely. New brine pools turning up in places no one expected them, including one set found astonishingly close to shore in 2022. Their chemistry didn't match the deep sea pools. Their microbial communities were different, and their existence suggested a more extensive subsurface fluid system than anyone had imagined. This raised a major question. If brine pools can form in places we never looked before, and if existing pools keep evolving, what is happening beneath the seafloor to feed them? The Red Sea didn't just have brine pools, it had an active brine system, and one that is still poorly understood. Now, we need to shift our focus to the chemical strangeness of these pools. Brine pools are not simply salty water. They are layered chemical environments, often with multiple distinct strata stacked like sheets. A sensor dropped through the surface shows instant changes in salinity, acidity, and temperature. These layers hold their shape because brine can be several times denser than seawater. Currents flow over them rather than mixing with them. This density is why brine pools don't just disperse into the ocean. They're too stable, they're too heavy, they're too chemically distinct. But when scientists revisit pools years or decades later, the chemistry often tells a new chapter of the story. One layer might now hold more manganese or iron. Another might be enriched in hydrogen sulfide. The temperature profile might have increased due to nearby hydrothermal activity. Microbial activity might have altered the redox state of the water. These aren't random fluctuations. They reflect changes in the hidden plumbing beneath the seafloor. New pathways opening, old ones closing, reservoirs feeding different mixtures of fluids upward. Some brines appear geologically young, formed by rapid dissolution of salt. Others look ancient, carrying signatures from deep, isolated aquifers. Sometimes these chemically distinct fluids sit only meters apart. And at the boundaries between layers, especially at the interface with normal seawater, lie the extremophile communities that make these pools biologically extraordinary. These microbes depend on exact chemical gradients. If you shift the chemistry, the community shifts with it. New gradients emerge, new microbial strategies take over. The deeper researchers look, the clearer it becomes. The chemistry of these pools is alive with change, revealing a subsurface system far more complex than expected. To understand why these pools evolve, we have to look beneath the seafloor. The Red Sea sits on a spreading center, a rift where magma rises as the crust pulls apart. That heat interacts with enormous buried salt deposits, dissolving them and producing dense brines. Some fluids originate deep within the crust, others come from those shallow salt bodies. Still others are mixtures of both. Salt behaves oddly under pressure. It flows, fractures, seals, and reopens. Because of this, the pathways feeding brine pools can shift over time. Not catastrophically, but gradually and chemically. A new fracture might introduce hotter brine. A blocked conduit might alter metal concentrations. And a nearby hydrothermal pulse might reorganize layers. These pools don't drain or vanish, but they do change, and those changes map the deep processes beneath them. So what does that mean for the creatures and the microbes living within or around these brine pools? Well, at first glance, a brine pool looks completely lifeless. The water below the halocline is so salty, so acidic, and so starved of oxygen that almost no complex animal can survive even brief exposure. Fish that accidentally cross the boundary often experience toxic shock, a rapid, overwhelming imbalance in salts, metals, and gases that shuts down their cells almost instantly. Their bodies sink into the brine and remain preserved, untouched by scavengers because nothing down there can feed on them. But right at that thin line between seawater and brine, a layer only a few centimeters thick, life manages to hang on in remarkable ways. First, the microbial fringe. This narrow boundary hosts communities of extremophile microbes, especially adapted to extreme salinity, sudden chemical shifts, low or no oxygen, and high concentrations of metals or hydrogen sulfide. They form mats, films, and tiny colonies that stretch along the halocline like biological contour lines. Each group occupies its own microzone, depending on what chemical gradient it can exploit. These microbes don't rely on sunlight or organic matter drifting down from above. They survive entirely on chemical energy, oxidizing sulfur, reducing metals, or processing methane. But microbes are not the only visitors to call these brine pools home. While brine pools are lethal to most marine life, a handful of non-microbial organisms have been observed near or at the edges of these environments. We've seen deep-sea amphipods skimming along the boundary. There have been rare polychaete worms grazing on those microbial mats. Every now and again, as we said, you'll occasionally see a fish carcass, preserved where they fell, but we have to admire them for trying. And in some newly discovered pools, there seem to be small crustaceans surviving right at the fringe. These animals don't go into the brine, they hover at the edge where oxygen still exists and where the microbial mats provide a concentrated food source. The halocline itself acts as both a barrier and, in a strange way, a refuge from predators that cannot tolerate the chemistry. One theme remains: this is a community shaped by chemistry. Because the brine's chemistry can shift from year to year, becoming warmer, more metal-rich, or more sulfide-rich, the microbial community shifts too. Sulfur oxidizers dominate one year, then the methane oxidizers take over the next. Maybe the year after that, metal reducers flourish when concentrations spike. The boundary becomes a living record of the pool's changing chemistry. This combination of deadly to almost all life and perfectly tuned for a narrow band of extremophiles is what makes brine pools so biologically compelling. The organisms that survive here do so by exploiting chemical conditions that would instantly kill nearly everything else, including the animals that accidentally wander too close. And because each pool has its own chemical fingerprint, the life at its edge becomes a unique miniature ecosystem shaped directly by the geology beneath it. The organisms living at the edge of a brine pool aren't just surviving, they're reacting to every chemical shift happening beneath the seafloor. When metal concentrations change, the community reorganizes. When temperature rises, new species appear at the fringe. Each pool becomes a biological sensor, recording changes in the deep plumbing we still can't directly see. And that's what makes these underwater lakes more than geological curiosities. They're dynamic systems, evolving chemically, biologically, and thermally, offering a rare window into the hidden processes shaping a young ocean basin. Which brings us to the bigger question: what can these changes actually teach us? Brine pools aren't static features, they're natural laboratories. Because their chemistry evolves over time, each pool captures a different phase of the Red Sea's development. Their temperature profiles reveal where hydrothermal activity is shifting. Their metal content traces how deeply fluids circulate through the crust. Their microbial communities respond to even subtle changes in chemistry. For microbiologists, these fringe ecosystems may resemble the earliest forms of life on Earth, organisms using chemical gradients long before photosynthesis evolved. For geochemists, brine pools show how fluids move through spreading ocean crust, how salt dissolves, and how metals concentrate, offering clues to mineral formation and volcanic processes. And for climate scientists, understanding how brine pools trap or release methane-rich fluids may refine models of greenhouse gas behavior in deep ocean basins. Every new pool discovered expands the map. Every change measured adds another piece to the puzzle. But even with all this progress, the system is still largely unmapped, and its behavior often defies our expectations, which leads us to the deepest mystery of all. After decades of exploration, the Red Sea brine pools remain one of the most surprising and least understood features of the deep ocean. We know they form where rising heat meets buried salt. We know their chemistry shifts as subsurface pathways open and close. We know new pools can appear in places we never thought to look. And we know the life that thrives here is unlike anything found in ordinary marine environments. But the essential questions remain unanswered. How extensive is the hidden plumbing beneath the seafloor? What controls the chemistry of each pool, and why does it change so differently from one basin to the next? How many brine pools have not yet been discovered along this rift? And are these evolving ecosystem snapshots of a young ocean basin still wiring itself together? Every expedition pushes the boundary a little farther, but the Red Sea keeps its secrets close. Its brine pools are not relics, they're active, changing systems tied to processes deep in the Earth's crust. And for now, the only way we understand them is by returning again and again, watching these underwater lakes shift layer by layer, molecule by molecule, as the seafloor beneath them continues to reshape itself. In a world where many ocean mysteries fade with better technology, the brine pools of the Red Sea are the rare exception. The deeper we look, the more questions we uncover. Stay curious, stay current, and thank you for watching.